Imagine you and a friend both want to draw a random network. I said, and a friend.
Oh yeah, come on in. Hey, how you doing? You know, I do know, because I'm you.
Okay, whenever you're ready. Look, here's what you do.
Oh yeah.
Both people draw a collection of vertices, and then, for every pair of vertices, they flip a coin to decide whether or not to link those two vertices with an edge. Initially, the two networks look very different, but were these two close friends to carry on for a countably infinite number of vertices, they would end up drawing exactly the same network. And not just a network that seems similar, the identical network. This is the radograph. Okay, plan 2, folks. I want you both to draw a new random graph that's different to the previous one.
Now my plan to make it different is instead of flipping a coin, I'm going to throw a dice, like on 2 different axes to make it random. And if the top number is a 6, which is not, I will then join the next 2 edges together, which means now there'll be far few edges. So I just did that one, that's not going to be drawn. So in theory, I should end up with, not a 6, a very different network. So my plan is I've numbered all the vertices, and whenever I pair up 2 of them, I'm going to get the smallest number and find that position in the other number in its binary representation, and if it's a 1, I'm going to link them. If it's a 0, I'm not. So the first position in 2 is a 0, so I don't link them. The first position in 3 is a 1, so I'm going to link those. First position in 4 is a 0, not linked. First position there is a 1, so I link those. Now I do all the second positions. So the second position in...
Well, that's all well and good, folks, but it turns out you are both once again drawing exactly the same network.
Unbelievable.
Yes, it turns out the radograph is inevitable.
Hey, caught it. Thanks.
Even though random graphs may start off looking different, the longer you carry on making them, the more similar they become. And, should you have infinitely many vertices in your random graph, it will always converge to be exactly the same.
Yes, there is only one random graph. It's inevitable. No matter what you do, you end up with the radograph, named after mathematician Richard Rado, or Rado. Anyway, people before Richard discovered this graph, and people after him have and will continue to, because it is inevitable. So I think of it as the randograph. And you won't hear graph theorists really talk about imagine a random graph. They will say imagine the random graph. There's only one, and you can't avoid it. It's always there, lurking behind you. And it is the creator of all other graphs. Any graph you think of. So here we have the Peterson graph. Big fan. You can think of your own favorite graph. Somewhere in the radograph, this set of vertices exists exactly like this as a subgraph. And not just that one. Boom! Herschel graph. That's in there too. Any finite, or indeed countably infinite graph you can imagine is in there somewhere. It's inevitable, and it contains all. If networks had a god, their deity would be the radograph. And that could be it. That could be the end of the video. Crazy mass fact. Isn't that phenomenal? So if that's all you're here for, you can stop watching now. Although before you do, Jane Street is sponsoring the video, and I want you to know internship applications for the Hong Kong office are now open. I'll talk about more about it at the end of the video. I've been there. Wonderful office. You don't have to be in Hong Kong to apply. Details later on. But the point is, while we could end the video here, wouldn't it be more satisfying to prove all those things I just said? Because with one additional fact and a little bit of thinking it through, you can both convince yourself that the radograph contains every other graph, and you can convince yourself that it's inevitable. So we're going to do it. That's inevitable. Okay, now it's just us, people taking it seriously. We have to define some terms. I've been real fast and loose. I'm calling things either networks or graphs. And that's because your average human would call a collection of nodes joined together by edges a network. Whereas mathematicians have decided we're going to call this a graph. So that's why I flip between them. Sometimes network makes more sense, but I want to use graph. So if you look things up afterwards, you've already got the correct terminology. And we're talking a simple graph. So for any pair of vertices, which is what we'll often call nodes, because then if we call them vertices and edges, the language is ready for making this equivalent to shapes like polyhedrons. Anyway, so for this pair of vertices, you either have them linked together or you don't. That's it. You can't have something like a double edge. I mean, in other situations, this is fine, but in a simple graph, no. None of that. And none of this going out from one vertex and coming back in. No, none of that. For every pair, there either is an edge or there is not an edge. And I've been referring to it being an infinite graph. What I strictly mean is a countably infinite graph of indistinguishable vertices. So that means, first of all, for every whole number, all the countable numbers from 1 up to infinitely many, there is a vertex for that. So there's more than 7. There would be infinitely many of these with an exact correspondence to the counting numbers. And they're indistinguishable. So while I have numbered these, they're just temporary labels to help us keep track. There's nothing inherently 4 about that vertex. At any point, we could relabel them. The labels are just a convenience. Technically, you cannot distinguish between the vertices other than what edges there are and there are not. And that's just it. The board can go away. Look at that. Magic. I'm using my foot. So with that in mind, as long as you're happy with dealing with the notion of infinity, which can be a little annoying, but that's okay. Check out my video about infinitely many $1 bills. And you're okay following the logical steps of graph theory, there's no other prerequisites. We've got everything we need. We can prove these things. You can convince yourself everything I've said is true. We can achieve all of our hopes and dreams that pertain to this specific problem using a single property of an infinite graph. It's something called the extension property. And what the extension property means is you can take any collection of vertices you want from an infinite graph, and let's call them collection A. You can then take a second collection of any other vertices you want and call them collection B. And the only restriction is there cannot be a vertex that is in A and B. So you pick your own A and B arbitrary vertices, as many or as few as you want. The extension property means that out there somewhere is at least one more vertex, which is not in A or B, and it has the interesting characteristic that it shares an edge in common with every single vertex in A, but absolutely none of them in B. So you can pick any collection of vertices in A that you do want to all be connected to this new vertex, and any vertices in B that you don't want to be connected, and you're guaranteed to have at least one vertex which fulfills your wishes. And that's it. If we can show that a graph has the extension property, not only does that mean that it definitely contains every other graph as a subgraph somewhere, but it also means that any two graphs that both have the extension property are actually the same graph. We'll deal with the coin and the dice graphs in a moment, but first of all, we'll do the one where we use the binary digits to decide if we're going to link two edges or not. And here I've got my categories A and B, and they're numbered. And again, the numbers are arbitrary. We've just numbered all the vertices in some order, doesn't matter what.
A quick recap on the binary method for edge rules. You have two vertices, you pick whichever one has the lowest, albeit arbitrary, number. That number will be our place position value. We then look at that place position in the binary version of the other vertex's bigger number. And if that position in the bigger number is 1, then we join those two vertices together with an edge, and we don't if it isn't. And what I'm about to do next is show for these two sets we can always find, by a method of construction, a vertex outside of them that fulfills the extension property requirements.
And we look at all the numbers in here and we think, okay, there's going to be some other vertex out here, number n, that links to these but not those. So first of all, we just guarantee n's going to be bigger than any of these. So it's going to be bigger than 6. 6 has 3 digits in binary. So long as this has more than 3 digits in binary, it's going to be bigger. And then we go through and we construct our number. You know what? I'm actually going to give it 6 digits in binary. And then we go through and we fill in the numbers to make it do what we want it to do. So we want it to link to 1, so we put a 1 there. We want it to link to 3 and 4, so 1's there and there. We don't want it to link to 2, so we put a 0 there. We don't want it linked to 6, we put a 0 there. And then the rest, whatever we want. So we happen to not care about the 5th one. I don't know. Let's make that 0. Let's be a little bit lazy, which means now we've got the number 13. So it turns out n equals 13, vertex number 13, if we were joining vertices up with that binary matching rule, would fulfill our extension property requirements. And that would work for any set of numbered vertices in A and B. You could definitely find another numbered vertice which links to everything in A but nothing in B, and you're doing that by construction. The probability ones, a little more hazy. Okay, for the coin flip graph, we're going to start with the same two categories of A and B, and then we're just going to pick some vertex out here somewhere. Let's say that's vertex, I don't know, vertex I. There's a probability vertex I is the one we're after. There's a probability it's not. It's probably not. We could say, actually, the probability of the vertex we're after not being I is equal to some value x. And x is between 0 and 1. It can't equal 1 because there is a chance it's the one we're after. It's just probably not. So we'll look at another one. Here's a second vertex. We'll call that vertex j. There's a probability that's the one we're after. Probably not. The probability that it's not I or j equals x to the 2 now, because we've got 2 of them. And the key thing here now is that x squared is going to be smaller than x, because x is less than 1. So if we were to pick another vertex at random, k, and then check is it not I, j, or k, we're now up to x cubed. It's even smaller. And if we had n different vertices that we've looked at, the probability that we've not found the one we're after yet is x to the n. And as n approaches infinitely many, x to the n is going to approach 0. So the probability, after we've checked infinitely many other vertices outside of A and B, that we haven't found the one that we're after that satisfies the extension property, is 0. So the probability that vertex does exist is 1. It's almost certain, which is subtly different to guaranteed. I don't want to get into probability like measure theory stuff. There's always like some malicious graph, like what if there were no edges at all? I don't care about that. The point is, if you've got infinitely many vertices that are joined together randomly, it is almost certain, with probability 1, that the extension property holds. And we haven't picked a value for x. That's anything between 0 and 1. So this logic holds for coin flips, it holds for rolling a dice. As long as there's a non-zero chance you've linked any given pair of vertices together, you will have the extension property almost certainly, with probability 1. And who can ask for more than that? The point is, all random graphs converge on the Rado graph with the extension property. We now know that all our graphs have the extension property, and we'll deal with proving that they're all the same graph in a moment. It's easier to first of all prove that the extension property implies all other graphs are subgraphs. So as an example, here I have a nice friendly small graph. I have the diamond graph, and I've numbered the vertices 1 to 4. Again, that's arbitrary. You can number them however you want. We're going to prove that this, indeed any other graph, is somewhere in the Rado graph. And we do that by building it up one vertex at a time. So the lowest numbered vertex, 1, just pick a vertex. That's going to be our corresponding number 1. Then, to fill in the second vertex, we work out what we need it connected to. So we've already got 1. So we do want it connected to 1. So we're going to call that category A. And we don't want it connected to, well, we haven't got anything else yet. So strictly speaking, B would be a null, some kind of null set over here somewhere. That is just completely empty. We don't care. And we know by the extension property, we can definitely find a vertex that's connected to everything in A and nothing in B. So now we've got 2. Now 3 has to be connected to both of the previous ones we've already got. So now we redefine A to not just be 1, but to be 1 and 2 at the same time. And B is still the empty category. And we know by the extension property, we can definitely find a vertex 3, add it to the graph. And then we just keep going. Each time we want to add one more vertex, we define our categories A and B to force that vertice to exist. And we know by the extension property, it will. So 4 has to be connected to 2 and 3, but not 1. Give me a second. Right, I've defined 3 and 4 to be in A and 1 to be in B. So we know by the extension property, we can find a vertex that's exactly the same as what we want for our 4. Links to both of these, but not that one. And then we just keep going. For each new vertex, redefine A and B. It guarantees we can find the next vertex down, fill it in, repeat over and over and over. As long as we have the extension property, we can build up any graph we want of any size of our choosing. Finally, I have 2 infinite graphs that are generated however you want, coin flips, binary, your choice. The point is, they both have the extension property, and we're going to prove they're exactly the same graph. And we're going to do that by gradually putting each of them into a region within the graph, and we'll keep the 2 regions identical until they cover all of both of the graphs, showing that the whole graphs are identical. Okay, just bear with me. Here's how we're going to do it. First of all, we'll use the lowest numbered vertex in each of the graphs. Doesn't matter how you number them, just assign a whole number to every single vertex and put vertex 1 and vertex 1 in a region. Doesn't matter which, because they're not joined to anything else in the region. We're now, on the first graph, going to move in the second lowest numbered vertex, which may or may not be connected to the first one. In this case, it is. And we have to do the same thing on this side. So using the extension property, we find another vertex that is connected to the first one, may not be the second one, and we move that in. We then pick the next lowest number vertex outside the region in this graph, check how it's connected to all the ones already in the region, move it in, and at the same time, use the extension property to find a matching one over here and move it in as well. And then find the next lowest on this side, move it in, find the matching one, move it in, and then we go backwards and forwards. And because each time, whichever one we move in on one, we can find a matching one using the extension property in the other one. And because we're going backwards and forwards, we're not leaving any unmatched. We will gradually match up all the vertices in both of these infinite graphs into pairs where each pair are identical vertices. And that's it. We can do that, and we can prove both graphs are identical. Now, again, this doesn't involve not getting too stressed out about infinity and these kind of matching things up. And if you've done stuff involving, you know, Hilbert's Hotel and matching stuff with countably infinite sets, you'll recognize this kind of matching approach. But it does work. As long as you're systematic, you can prove these are exactly the same graph. All infinite random graphs are the Rado graph. There's only one. So that is the Rando graph, and isn't it satisfying that we actually went through the explanation, the logic, the proof, and we took what were counterintuitive, weird properties and eventually made them, well, almost obvious. In fact, the longer you think about it, the more obvious they get, and the whole extension property is just kind of codifying obviousness. I mean, it's my theory. Any sufficiently well-explained mathematics is indistinguishable from being obvious. In some cases, a lot of explanation, but the point is, understanding things is its own joy. And if you enjoy learning things, oh, here comes a segue for you, because this video is sponsored by Jane Street, and they have opened their internships in their Hong Kong office. Yes, they do also have internships available in their New York and London offices, but they're specifically recruiting for curious, enthusiastic individuals to join the team in Hong Kong.
Jane Street are a quantitative trading firm who use techniques from machine learning, distributed systems, programmable hardware, and of course statistics to trade on markets all around the world. And they're currently accepting applications for internships in quantitative trading, software engineering, research, institutional sales, and naturally, trading. This one-of-a-kind internship experience runs from May until August in 2026, and during that time, you'll be surrounded by brilliant people from a diverse range of backgrounds and cultures who are passionate about what they do and eager to teach you what they know.
And when you're not working, you get to enjoy Jane Street's fantastic office in Hong Kong, join in the social events, and watch the guest speakers, which this year included me. I try to go out to Hong Kong as often as I can. I was there to see the most recent fleet, actually the most recent 2 groups of interns in Hong Kong. I gave a talk, I got to hang out. We ate pizza, we talked about maths. I had a great time. I think everyone else had a great time. Anyway, I always enjoy visiting the Jane Street office in Hong Kong. It's such a phenomenal city, and you'll get to enjoy living in Hong Kong while also hanging out with a group of like-minded people. All the details are in the description below, or use the QR code on the screen right now. But spoiler, here's some things you don't need. You don't need to have a background in finance. A lot of Jane Streeters were like you, no finance experience. They did the internship to find out what it would be like to work in the quantitative trading industry, and you don't have to be in Hong Kong already. Jane Street will fly you there. In fact, you don't have to already have a pile of money, because Jane Street will cover your travel and accommodation to Hong Kong, and they will pay you a salary. It's a paid internship for your time there over the summer. If you have a curious mind and a collaborative spirit, you will fit right in at Jane Street. Please do check out the details or pass them on to someone who you think will benefit from them. And huge thanks to Jane Street for sponsoring this video. Well, that's it. Thank you so much for watching the video. But before we go, for one last time, here comes the whiteboard again. Like magic. How's that even happening, huh? It was me. Oh, it was me the whole time. Yeah. And while we're here, if you've watched right to the end of this video, thanks. It's been a wonderful year. Next year, calculating pi on the moon. Yeah. And before the year's over, you can still sign up for a digital Christmas card from me. Yes, it's too late for us to post a physical card, but if you do sign up, we will email one to you. So that's it. From me and me, thanks for watching.